Hello everyone, I am Bharat Singla and welcome to CodeChef. Here we post tons of content on competitive programming. So if you are new to the channel, consider subscribing. Great, now let's get started. So I am back with yet another video on a yet another classic recursion problem. Today we'll try forming a recursive solution to find any number raised to the power another. Now, why only these problems, like the Fibonacci series, the factorial of a number, and exponentiation, and why not any random code shift problem? Well, that is because over time, these problems have turned out to be the best resources to make someone understand recursion. So they are no more problems, they have become the concepts themselves. A few possible reasons could be that the recurrence relation as well as the base cases here are pretty obvious and easy to figure out, as well as the code is very short, merely 2 or 3 lines. So hopefully this satisfies your curiosity that no matter where you study recursion from, why do you always find it being taught using these problems? So let's get back to business. So a to the power b is given by this formula here, that is a multiplied by itself b times. So we are going to compute a raised to the power b using recursion today. And now, assuming that you have already watched the previous 3 videos revolving around the idea of recursion, I strongly feel that you are now well equipped with it. So this time I want you to yourself come up with the recurrence relation as well as the base condition or conditions. So here's the solution. So notice that this part over here, this part is nothing but a raised to the power b minus 1, isn't it? A multiplied by itself b minus 1 times. And now since this is similar to this in terms of the structure, so we can use functions to define it. So let's say I have this function power of a comma b, that is essentially a raised to the power b. So this can be written as power of a comma b minus 1 multiplied by a, right? This is a here. So here we go, boom, we have this recurrence relation over here. And now since we are calling b minus 1, so we are always going one step down. So one relevant base case could be to take power of a comma 0 to be 1, right? We all know any number raised to the power 0 is 1. And we could have also taken power of a comma 1 to be equal to a. That would have sufficed as well. And notice that we only need one base case over here since we are only calling b minus 1. So no matter where we start from, we'll always converge into this base case, right? So here we have both the steps to solve any recursion problem. The first, the recurrence relation, and the second is the base case. Now, why do I say it to be a magical process? Well, notice that if you just try to solve the recursion problem as a whole, then it's very tricky, right? It could sometimes become very hard. But if we decompose it into these two steps, is it hard to find a recurrence relation? No, it's very simple as we saw here. Is it hard to find a base case? No, it's pretty easy as well. And now you can simply combine both these steps and code it out, right? So make sure that you first think of this step, then this step, and you already have the solution. So here I'm leaving the code as an exercise for you. And over time, I figured this out that we all learn better if, in lieu of just watching a video passively or reading a blog passively, we try to interact and brainstorm as well. So that's why I frequently keep on giving exercises, and the code for this recursive approach I'm leaving to you guys. Okay, so you might have heard of this term called efficiency. Efficiency of a program, in simple words, is nothing but how optimized your program is in terms of the time and the space it takes. So the difference between a good programmer and a great programmer is that the good one will simply try to code it out and somehow make the code work. But a great programmer will not just write correct code, but will also, his solution will also take less time and less space to run. So that's why instead of this recursive relationship, there's another very interesting and very wise relation, that is to split the powers into two. So I can use power of a comma b as power of a comma b by 2. and this squared. So let's take up this example that 2 to the power 4 can be written as 2 to the power 2 square, right? We know by the laws of exponents, if I divide b into b by 2 and then I square that, so it is essentially b only, right? So I can use this. And what if the power is odd? In that case, it cannot simply divide it by 2. So what we do is we floor divide it by 2. So we get 2 to the power 2 again. 5 by 2 is 2. If we floor it, right, this squared, but now we can also multiply it with 2 again. So this is 2 into 2 plus 1, which is 5, right? So I could check if the power is even. Simply take power of a comma b by 2 and square it up. If the power is odd, then again take b but floor divided by 2 and then multiply that with the base, that is a again. So this is a new recursive relationship. And how is this beneficial? Well, notice that if I call 2 to the power 8, it calls 2 to the power 7. This is for the original recursive relationship. Then this calls 2 to the power 6, so on till 2 to the power 0, right? Or let's say 2 to the power 1. So if this is the base case, so 2 to the power 1, and here it stops, right? But what if I call this new recurrence relation? So that is 2 to the power 8, that will call 2 to the power 4, which will call 2 to the power 2, which would call 2 to the power 1. So notice approximately how many calls are these two programs taking? Well, this one here is taking around B calls, right? At each point we are reducing it by 1. So this is taking B calls, right? And how many calls is this program taking? This is taking around log base 2 B calls. Why? Because at each point we are dividing B by 2. So the number of steps to reach from B to 1, if we constantly divide it by 2, is nothing but log base 2B. And which one is more efficient? Well, definitely this one is more efficient. Why? Because let's take up an example of 10 raised to the power 9. That's a huge number, right? But notice what is log base 2b. Well, that is merely 30. So from a billion, we brought it down to 30, and that's so highly optimized code, right? So this recurrence relation is much better in terms of the complexity, but again the code is a little bit more complex. So this time I'm again leaving the code as an exercise for you. But make sure to not make this mistake. That is to, let's say I have this function, right? And I call power of, using p as power. So I call a comma b by 2, right? But now don't write it like this. So power of a comma b by 2 multiplied by power of a comma b by 2 to square it up. So what's the loss in this kind of an equation inside the body? Well, notice that 3 comma 4 will now make two calls, 1 to 3 comma 2, 1 to 3 comma 2. And again, these will make two more calls, 3 comma 1, 3 comma 1, 3 comma 1, 3 comma 1. Right? So notice that anyways these two are going to give us the same result. So writing it like this is going to take similar number of steps only, right? So this is no optimization over here. Instead, use this. So you can use like a variable x, store it there, right? So store this in that variable, and then what you can do is instead of using this, you can return x into x, right? So this way you are only making the call once, and this is 3 to power 4 calls 2, which calls 1, right? So this is like the correct way to write it out. So I'm again leaving this as an exercise. If you still have any trouble in coding this out, you can definitely tell me in the comment section and I'll provide the code. So here we go, guys. We have this new recurrence relation, which is much more optimized, and here we have solved this problem, right? So this not just wraps up this video, but also wraps up the recursion playlist. Hope this helped build a strong foundation in recursion. But there are two important things that I wanted to convey. The first is that I highly encourage you to continue to the DP playlist as well, dynamic programming playlist. And why? Well, that is because dynamic programming is nothing but optimization over recursion, right? So anyways, if you continue to the playlist and you do not want to learn DP, you can still just watch the first half because the unoptimized part is recursion only. So it will help you strengthen your concept even more. And if it's not uploaded yet, it would be in some time. And you will also get this benefit of learning DP, right? So make sure to watch some DP videos as well because that will improve your problem solving skills in recursion and strengthen your knowledge and tighten your grip on it even further. The second important thing is that CodeChef educators take live sessions on Unacademy regarding these same competitive programming topics. Like I post these recorded videos, so there are some CodeChef educators who take live sessions on Unacademy, and they are the best in India. And to watch those live sessions, all you have to do is create an account on Unacademy, right? And you can just start watching them, and they are available for free. But you can also go for the paid plus subscription to get numerous benefits like full-time doubt solving, mental health, and the mentor is a 6-star and 7-star coder as well. You also get problem sets for each topic and whatnot. So opting for either of them, you'll need a code. So you can use this code Bharat27 to register if you just want to watch the live sessions and interact with the teachers. Or even if you are going for the plus subscription, then this code will help you get a 10% discount. So thank you guys. This winds up the video and I'll see you next time.